So we are going to do some problems before we close this session on extension theorem, isomorphism extension theorem. The first problem we are going to attempt is this. Let P be an automorphism from Q of pi to Q of pi defined by P of pi is equal to minus pi. Then find the fixed field of Q of pi this is our problem. Is Q of pi is actually transcendental over Q. So the simple extension of pi over Q is a field of quotients. That is polynomial in pi by polynomial in pi where R of x comma Q of x belongs to Q of x. So this is the curly bracket and this is a square bracket. So these are polynomials in pi where Q of pi is not equal to 0. So when an element is transcendental, this is how you form the simple extension. So this is a field now. Q of pi is a field. So Q of pi the field extension is the definition of fixed field. The definition of the fixed field is alpha belongs to Q of pi such that P of alpha is equal to alpha. It means the P does not move alpha. Those elements from Q pi which are not moved by P. But any of this alpha is in this form. So this is actually equal to, instead of R of pi, what I'm going to write here is A0 plus A1 pi plus dash dash AN pi to the power of n divided by B0 plus B1 pi plus dash dash BM pi to the power of m, where AI's and BI's belong to Q, and for some integers M and N. Well, where P of A0 plus A1 pi plus dash dash AN pi to the power of n divided by B0 plus B1 pi plus dash dash BM M is equal to P of alpha is equal to alpha. So this is equal to a0 plus a1 pi plus dash dash an pi to the power of n divided by b0 plus b1 pi plus dash dash bm pi to the power of n. Now, P of a0 plus a1 pi plus dash dash an pi to the power of n divided by b0 plus b1 pi plus dash dash bm pi to the power of m is equal to, we are defining pi by p of pi is equal to minus pi. So this will be a0 minus a1 pi plus a2 pi square plus dash dash minus 1 to the power of n a to the power of n pi to the power of n divided by b0 minus b1 pi plus b2 pi square plus dash 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 minus 1 to the power of m bm pi to the power of m, and that is equal to alpha. This is the definition of P. In order for this element to be here, this has to be equal to a0 plus a1 pi plus dash dash an pi to the power of n divided by b to the power of b0 plus b1 pi plus dash dash bm pi to the power of m. And this implies what? This implies a1 comma a3 comma dash dash a2n minus 1 is equal to 0. b1 comma b3 comma dash dash b2m minus 1 is equal to 0. Or we'll say these are all zeros. We don't need to say the end of this. So these are all zeros and these are all zeros. So what does that mean? In here you will have, so that means q of pi, the fixed field of P is equal to a0 plus a2 pi square plus dash 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 divided by b0 plus b2 pi square plus dash 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 b2m pi to m. This is actually a to n pi to n, where ai's and bi's belongs to q. And this is nothing but q of pi square. So the fixed field of q of pi over this automorphism is this. So q of pi p is equal to q of pi square. Let us do another problem. Let K be algebraically closed. sigma is an isomorphism from K to a subfield of K. It's an isomorphism. E is an isomorphism. This is possible because when K is infinite, this is definitely possible because the sigma doesn't need to be onto. It's a 1-1. If K is algebraic over the image of K, then sigma is an automorphism. That's what we want to prove. So let's draw the diagram here. So this is our K, and I'm going to write another K here. And this is our sigma of K. So sigma is from K to a subfield of K. That implies sigma of K. So this is our sigma. So sigma is an isomorphism, so we can talk about an inverse isomorphism. So we are going to see that is from sigma of K to K. So this is sigma inverse only from here to K, because this is K. We are actually, this is going in this direction. So inverse is going from here to here, and that's what exactly I said. So sigma inverse is a isomorphism from sigma K to K, is an onto isomorphism, meaning every element of K is already mapped, and this is algebraically closed. So that means K is algebraically closed, implies K closure equal to K. So these are all equal to K closure equal to K closure equal to K closure. Now just consider this portion. K inverse is an isomorphism from sigma K to K. And K is an extension of sigma K, algebraic extension of sigma K. So sigma inverse can be extended to an isomorphism from K to a subfield of K. So sigma inverse can be extended to an isomorphism from K equal to K closure to a subfield of K equal to K closure. But sigma inverse is already onto. See, you are talking about an extension from here to the same field, which is not possible because sigma inverse is the sigma inverse of sigma k is whole of k. That means this has to be here. And that implies sigma k is equal to k. And that implies sigma is an automorphism. What is an automorphism? Automorphism is an isomorphism from K to itself. We'll do another problem. Let E be an algebraic extension of F. Then every isomorphism from E to a subfield of F closure can be extended to an automorphism in F closure. This is a very powerful result. To prove this, we are going to use the previous result. The previous result is K is algebraically closed and there is an isomorphism from here to a subfield of K, and if K is algebraic over sigma of K, then sigma is an automorphism. So we are going to make use of this result here. So here what is happening? There is an F closure here, and there is a E here, and there is an F. E is algebraic extension of F. And there is another, there is an isomorphism from same F closure. There is an isomorphism from E to a subfield of F closure. Every isomorphism from E to a subfield of F closure. So this is our this is sigma, and this is our sigma of E. So what is happening here? Sigma is any isomorphism from E to a subfield of F closure. So this can be extended to an isomorphism to F closure. So sigma is from E to a subfield of E, a subfield of F closure. So sigma, and what else? F closure is algebraic over E. That implies sigma can be extended to a toe from F closure to toe of F closure, a subfield of F closure. And F closure is algebraic T of F closure, because this is a closure of F. So any subfield of F closure is an extension, algebraic extension of that subfield. Now we apply this theorem. So here our sigma is this tau, F closure is the K, and this is our sigma K. Tau of F closure is sigma K. And K is algebraic over sigma of K. Here F closure is algebraic over tau of F closure. That means tau is an automorphism. We'll do another problem. Let E be an algebraic extension of F. Then E closure is isomorphic to F closure. So let us start with an identity map. This is our F closure, this is our E, and this is our F. E is an algebraic extension of F. This is our F closure, and there is an identity map from F to F. So let I from F to F be the identity isomorphism from F to F. Because E is an algebraic extension of F, you can extend to a sigma from E to a subfield of F closure. This is our, so I can be extended to sigma from E to sigma of E, a subfield of F closure. Now F closure, sorry, E closure is algebraic over E. So that means there is an E closure somewhere here. So I'm going to write it as a separate diagram. F closure is here and there is an E closure here. And E somewhere here. So this can be extended to F closure. This sigma can be extended to F closure. So that is probably a tau. This is again F closure. This is our E closure. Sorry, not the E closure. This is a tau of E closure. So sigma can be extended to a tau from E closure to tau of E closure, a subfield of F closure. Now consider the inverse of this. So we'll draw another diagram here. We have F closure here and we have toe of F closure here, toe of E closure here. So 2 E closure. This is actually E closure. So this is actually toe inverse from toe of E closure to E closure. And this is an onto isomorphism. So T inverse is an onto isomorphism from toe of E closure to E closure. Now F closure is algebraic over toe of E closure. F closure is algebraic to toe of E closure. So we can extend. Toe inverse to F closure to a subfield of E closure. But toe inverse is already onto, and that implies toe of E closure is equal to F closure. See, you cannot extend here, because if you extend it here, then you have to take a larger field from here, which is not possible because this is already an E closure. So that implies, there exists an isomorphism from E closure to F closure. That means E closure and F closure are isomorphic. We'll do one more problem before we complete this topic on the extension of isomorphism theorem. Is the result which we are going to prove is the closure of the simple extension of q of root pi is isomorphic to the closure of q of x. This is not the ring of polynomials in X. This is actually the field of quotients of ring of polynomials. Or this is same as Q closure of X. These two are same, one the same. So the way we are going to prove one is that we are going to create an isomorphism between these two. For that, first thing we have to do is claim. The first claim is root pi is transcendental. That is because if root pi is algebraic, well, we'll clarify some more thing here. Transcendental over Q, because if root pi is algebraic over Q, then root pi is an algebraic number. And the collection of algebraic number is a field. The collection of algebraic numbers is a field. That implies square is an algebraic number. That implies pi is an algebraic. Which is a contradiction. Because we know that pi is not an algebraic number. So root pi is transcendental. So let us define a map from q of root pi to q of x. When you define a map, you can define the map by the generators. So the generators are 1 and pi. 1 means it's an element of Q. So defined by phi of A is equal to A for all A in Q. That means the generator is 1, and phi of root pi is equal to x. Then phi is a isomorphism. Verify. That's an exercise. Now we'll see we have q of root pi here and q of root pi closure here, and there is a map from here to q of x, and that is our phi. So q of root pi closure is an algebraic extension of this. Q of root pi closure is an algebraic extension of q of root pi. So phi can be extended to an isomorphism from q of root pi closure to a subfield of q of x closure. This is our q of x closure, and let that be tau. And this actually is going to be, we'll have another field here which is tau of q of root pi closure. Now we can talk about the inverse of tau. So that is from this subfield, that is tau of q of root pi closure, to this is actually tau inverse from here to the whole of root pi closure, and this is an onto function. Okay, so we can extend this one to the closure of this, because q of x closure is algebraic over this. So from to subfield, actually this let it be that isomorphism tau. So tau inverse from tau of q of root pi closure to a subfield of q of x closure is an onto isomorphism. This can be extended to q of x closure to a subfield of q of root pi closure. But sigma tau inverse is already onto, and that means tau of q of root pi closure is equal to q of x closure, and that is again equal to q closure of x. Both are same. So that is a proof of this. So that means q of root pi closure is isomorphic to q of x closure and q of